Good morning. My name is Paul Alemany, and today I'm going to present you a peer-to-peer blockchain-based NFV service platform for end-to-end network slice orchestration across multiple NFVA domains. This presentation is divided in five sections. The objective, the main concepts in order to understand the context of this presentation. Then I will enter into the focus of this presentation, which is the design of the architecture that I want to present. And finally, the last two sections, which are the experimental evolution that we did in order to demonstrate the feasibility of this the architecture, and the conclusions. First of all, our objective for this paper was to demonstrate that it is possible a different way of managing the network slicing resources, and instead of using a hierarchy architecture in which there is an element on the top managing the network slicing resources across all the multi-domain network, the idea is to create a network of peers, a peer-to-peer network, in order to make an architecture that in which all the network slice managers are equal one to each other. In addition, the second objective is, and to reach the first one, we aim to use blockchain into an NFV environment in order to it's the tool that will allow us to avoid this central point of authorization or central point of hierarchy. The main concept to use in this paper. First of all, network slicing. Network slice is a set of network services that are interconnected one to each other, and altogether they create a virtual network that is deployed over the physical network in order to give a specific service. Network slicing makes use of two types of data objects: network slice templates, which is the definition of the slice, which services are inside and how are they interconnected one to each other, and network slice instance, which is the descriptor with the instantiation of all the services composing a specific slice. So we might have different network slice instances for a single network slice template. The other concept to keep in mind is blockchain. Blockchain is a geographically distributed database in which all the peers involved, they create a mesh network and they share the same information. So if there is any new information to add or to modify, it has to be approved by all the peers before it is placed into the database. As its name says, the idea of this database is a set of blocks of data that they are interconnected one to each other, as you can see in the image. And the way to interconnect one to each other is using hash. Based on the information within one block, for example, block one, the peers create a hash, and then when they start the second block, they relate the first block with the second through this hash. The main characteristics of blockchain are the fact that it's distributed, so there is no central authority. First point to use it on the final objective of this paper. It's a secure technology in the sense that the peers use a private public keys encryption when they add information into the database. And as previously said, it's public in the sense that all nodes know all the information, and so it's a transparent system. It's not possible to, or it's quite impossible to cheat the system and modify a piece of information that was previously accepted by all the peers. With the main concepts presented, I'm going to go into the design, the architecture that we want to present, which is the following. First of all, on the left side of the slide, I want to present the architecture that bring up the idea that then we have on the right side. As you can see, there is an hierarchical architecture managing the resources across the different domains, optical networks and computing resources and so on. And what we wanted to avoid is this central point of view or central point of failure that might have a hierarchical architecture. As you can see on the left side, there is a global NFV service platform over controlling all the domains and even over of domain NFV service platform. In our case, what we did was that each domain had its own architecture, and on the top of each domain there is a network slicing manager, and they are this piece or this functionality are the peers of the blockchain that will control and manage the different slicing resources that are placed around all the network, the different domains of the whole network. With this architecture in mind, the next slides are presenting how the network slicing managers speak among them through blockchain in order to deploy an end-to-end network slice across the whole network. So if we have a vertical that requests a slice, we have a vertical that wants to deploy an end-to-end network slice, okay, first of all request to its slice manager. From now on we will call it a slicer. In this case, the slicer A, the domain A. It requests all the network slice templates available either in local and in the blockchain. So slicer A receives the request, asks for the network templates placed in the blockchain from other domains, and once it gets this information, sends back the whole information, local and blockchain templates, to the vertical. So the vertical can decide which templates to use to create the end-to-end network slice. Excuse me. Once the slicer receives this request, it starts creating the network slice instance data object that we presented previously. So looking where each template is, in which domain each template is, and once this information is known, or the slicer knows this information, can start requesting, depending on which domain the templates are placed, their deployment. So in the case that the template is in the local domain, the slicer itself will request to its NFV orchestrator to deploy the service and the elements in it. On the other side, if the template to deploy is in another domain, then the slicer will go through the blockchain, steps 9 and 10, and then blockchain will warn all the other slicers in the other domains, and the one that will be the owner of the requested template will get the event, or will accept the event, and start the instantiation process of each template in each domain. Steps 10 and 12. Meanwhile, blockchain answers back to the slicer A in order to confirm that the transaction within the blockchain has been done correctly. With all the templates, all the templates composing the end-to-end network slice being instantiated, from now on we'll call templates as a piece of as a slice of net, okay, as a piece of the end-to-end network slice. With all these slice subnets being instantiated, the slicer A keeps checking their status. If the local network slice subnet is instantiated, then the NFBO orchestrator will inform the slicer A, and this will update its local information. On the other side, if a blockchain or if a slice subnet in another domain is instantiated, is ready, the NFBO on the other domain will inform the slicer of that other domain, and this will update the blockchain. Once the blockchain receives this updated information, answers back in order to confirm that the transaction was well done, and again sends an event to all the slicers, and the one that wants to manage or is required to manage this event will get the event, will take it and update the information in its local network slice instance descriptor. When if none is updated, the slicer keeps waiting, as it said, 13 or 21 shows. But if all the slice subnets composing the end-to-end network slice are ready, then the slicer I will inform the vertical in order for this to start using the end-to-end network slice. With the workflow presented and the architecture design presented, let's go into the experimental evaluation. But before, in order to, as a piece of information, I just want to explain the reason why we choose a specific blockchain. There are different options in the market: Bitcoin, Ethereum, Hyperledger, which are the three most known, but we choose Ethereum. First of all, because Ethereum allows the development of decentralized applications using smart contracts. This means that you can create an application into the blockchain using this smart contract, which at the end is a set of functions that you can program. And so when you ask something to the blockchain makes reference to this to the smart contract. The blockchain takes this smart contract, checks the function that you require, and modifies or adds the information sent. Also, another reason to choose Ethereum in front of the others is because Bitcoin, for example, takes some minutes to encrypt a block and keep the information inside the database, while Ethereum requires a few seconds. The use case, as you can see, the idea is that we deploy an end-to-end network slice composed of two templates, NST1 and NST3. And in order to demonstrate that the whole blockchain affects the whole deployment of this end-to-end slice, we take 5 time samples. When the slice request arrives to slicer I, when the slicer A requests to the blockchain, the deployment of another slice in another domain. Then when this request arrives to the slicer B, and this starts to deploy its template, then once this is deployed, slicer B informs blockchain this moment. And then finally, the fifth time sample that we take is when the whole end-to-end slice is done. Playing with these time samples, we can find the difference of times and how blockchain affects the overall deployment. In here, just to present, I present the proof or the traffic, the demonstration of the workflow that I presented before. Essentially, we add the templates through each vertical with each slicer. Then these templates are updated to the blockchain using transactions I and B here down. Once a vertical requests a slice, requests the instantiation of the slice, and starts the instantiation of the slice in another domain, in transaction 3C, sorry, and the instantiation in a local domain, this one. When both templates are updated, the transactions or the request reach back to the network slice A, and the information is updated. In this case, this is the local, and transaction D here is the one coming from the blockchain. Based on the times that I presented before, which we can see that the values, or first of all, before entering the times, to understand better these values, this graphic, the deployment time is so short because we emulated all this process, in the sense that the deployments, which will affect mainly on this moment, on this column 3 and 5, were placed to 0, basically to see exactly how blockchain affects the overall time, which we can see with columns 2 and 4. So based on all this, we can see that as in previous deployments with it, and in previous deployments with it, the time was around 660 seconds, adding 11.5 seconds, which is these two columns plus their standard deviations. We can see that we add a 1.7% of time, which is not so much compared to the 660 seconds when we use virtual machines. In container-based, on the other side, we have a more important increment, but still it could be acceptable based on the total time. Finally, the conclusions is for this paper. Essentially, we presented an Ethereum block. We presented an architecture that uses blockchain to manage different network slicing resources across different domains. And we presented a traffic analysis and some set of results that affirm that this architecture could be feasible in a multi-domain network across a transport network. At this point, this is all from my side. So thanks for your attention. And if there are any questions, I will gladly answer them.